Good afternoon, everyone, and welcome to my tech talk, the Quantum Brutalist, where we are going to be brutally realistic about all the challenges we have to achieving real societal benefit from quantum computing. You know, a couple years ago, I was at a World Economic Forum mashup. It was the cybersecurity practice and the quantum development network, and one of my collaborators said, you know, we want to talk about how hard it's going to be to achieve a quantum benefit. You know, it's kind of like landing a space probe on another planet is hard. But there's landing on the moon hard, and there's landing on the sun hard. And you want to know the difference between those two things before you get deep into the program. So we're going to be brutally realistic. Optimistic, that's for investment bankers. Pessimistic, that's for economists, but we're engineers, and so we want to be brutally realistic about what it's going to take to achieve this technology. Now, there's probably no more forward-looking area that we will talk about here at Discover in Las Vegas than quantum technology, so forward-looking statements, you know, buyer beware, but also we want your feedback. The real reason that I come to Discover every single year is for conversations, for you to give us that unvarnished feedback where we're missing the mark, where we're hitting the mark, how are we doing, what should we be thinking about. So please take advantage of your app to give us feedback on the session. So we're going to dive right in. So one of the questions I always get asked about quantum is, the first one is always where? Where in the universe, where in the enterprise computational portfolio will quantum be advantageous? And we're going to go all the way back to the source. Nature isn't classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. So that was 1982, Richard Feynman, Nobel laureate, probably the most famous physics teacher in the entire world, and I think he was right on both accounts. Because when we are talking about quantum computing, we're talking about being able to engineer, to do research, to reason over systems where the physics that dominates the equations is quantum mechanical, is probabilistic. This is not Galileo, this is not Euclid, this is not Newton, it's Dirac, it's Schrödinger, it's Einstein, and we want to have that same facility, we want to have that same ease of use. So let's talk a little bit again about where. You know, what are the criteria that make a good candidate for quantum utility? Where should we be looking first? And the first thing we want to think about, I want a problem where I take a little bit of information, just a little bit of information, and second, I want to understand where's that algorithm that takes the superpowers of quantum mechanics, superposition, interference, entanglement, and has that quantum algorithm that can take that and without a lot of supervision, without a lot of manipulation, it can explore the solution space, and finally, give me that little answer out. And even better is when that little answer is something I can check really easily. That tells me this is the kind of space I should look. Now, back to Professor Feynman, science, chemistry, physics, condensed matter physics. Wouldn't it be great if I didn't have to pour a test tube into a beaker to figure out if something was a suitable candidate for the next generation battery chemistry? Wouldn't it be great if I didn't have to smash two protons together at just a fraction under the speed of light in order to understand the behavior of the gluons and the quarks inside of that, tiny mechanical system? So that's where we should be looking. So when we think about potential applications of quantum computing, I'm going to divide this up into two segments here. One has quantum data, and you say, where do I get quantum data? I get quantum data from a quantum physics experiment. I get quantum data from a quantum sensor. I can actually get quantum data from another quantum computer. And then there's classical data. That's the data, all the sensors, all of the data, all the things we see out on the show floor, all running on classical data. So if I want to simulate quantum systems, or if I want to do machine learning on top of quantum data, that is where we really see, this is where the applications are going to lie. Quantum chemistry, material design, drug discovery, fundamental physics. You notice everyone here is wearing a lab coat. They're just like all my colleagues over at the HPE labs demonstrations. They're all there, you know, they're used to experimental science, and that's really where we should look for those advantages first. Now, what about that classical data? Because I've heard, what about optimization? What about artificial intelligence? Isn't quantum going to be helping me solve those problems? And we think about financial modeling, we think about logistics, we think about weather forecasting, traffic optimization, machine learning, large language models, and then, but remember, my first criteria was a little bit of data in, and what are these? These are all massively data-intensive problems, and that's the rub. If I'm doing quantum machine learning on quantum data, provable exponential speed up on the algorithm, and that was that second criteria for me. Here, though, that's the problem, is I have to take all that classical data and I have to convert it. I have to get it into the quantum dimension, into the quantum realm, and that will eat up any potential advantage I have. So there's still research on something we call a quantum random addressable memory, which isn't quite what it sounds. What it means is I can take all that classical data and I can put it into a machine and I hit the button and boop, pops out an entangled quantum state that represents that data. Until I get to that efficiency, then we're going to have to look elsewhere. Fortunately, we have somewhere else to look, and that is quantum-inspired acceleration. So physics-based accelerators, but the classical physics behavior, and we have some of that research going on at Hewlett-Packard Labs, where we're looking to see what else we can do to accelerate these data-intensive problems, taking a page from quantum, but using different physics to accelerate it. Now, the one that fits every one of these criteria inside of that classical data is breaking encryption. So that is a little bit of data, 240 bits of an RSA cipher. What comes out? The two integers that make that prime number when they're multiplied together. So understanding how we do that. So this is the most important thing for every one of us here at Discover in 2025. This is the material outcome of quantum that we weren't waiting for, but we'll have to anticipate and begin to plan for. Higher banking fees, higher defense budgets, more expensive healthcare, because on all of those human and security and privacy intensive applications, we're going to need to understand how we move beyond current cryptography to post-quantum cryptography, and we'll talk about that journey that you should be starting in a couple minutes. So, the takeaway about where. It isn't a competition between classical supercomputing and quantum computing. When we've been working with our team at the HPE Cray, the supercomputing team, they've been inviting us, for the last 5 years as we've sort of come back into quantum. We had some low-level quantum research at Hewlett-Packard Labs back about 15 years ago, and that team put the work on the shelf to pivot over to large-scale integrated photonics because picojoules per bit from chip to chip or cabinet to cabinet, country to country, much more material for the enterprise outcomes than quantum has proven in that intervening time. But back after we acquired both SGI and Cray, we melded those teams together, talking to those customers, say, I love what you're doing with the exascale, but for the one after that, where do I plug the qubits in? So this is really the customers asking us, give us that hybrid system, because really what they want here is they want to stop doing physical experimentation. I think of our own disciplines at Hewlett-Packard Enterprise and the engineering we do, finite element analysis, nonlinear circuit analysis, and computational fluid dynamics. It doesn't matter if you're an electrical, a thermal, a mechanical engineer, you use these tools because you can do what would have taken prior generations a lifetime of experiments in the lab, and you can do it in an afternoon, and now you can have your AI agent sift through all of those physics experiments and give you a great engineered system. And really, this is what we want to get to with quantum. So when multi-physics is including both classical physics and quantum physics, then we need both classical computation and quantum computation melded together. And also, when we think about that quantum device, we know it has to be encased, enshrouded, it has to be fed, cared for, made productive, and all that takes a tremendous amount of classical computation. So it's not a competition, it is an opportunity for collaboration, and that's really what we want to do. So the next big question, we actually talked about where, next question is when. And this is really material because we want to know, should I make this investment? And whether that is investing the next $1 billion at a national research program, or the conversation you have over your kitchen table about what you recommend your kids to begin to pursue in school, when? When is this going to be material to the enterprise? And for us, again, we're going to take the page from where. The where is chemistry, the where is physics, the where is condensed material science. And we think about this graph. Now, the way to read these, the orange line is where we started before we formed a combined research community. And so you can see this is from seconds up to hundreds of years. And that orange line, oh, those are pretty tough because it's saying I'm still, even after we do all our work, we're still about between a month and a year to do an important element of chemistry. This line right here is the line over here. I'm going to use Frontier. I'm going to use El Capitan. I'm going to use that supercomputing prowess that we already have. That's all classical, and I can solve it well enough. I cross over this threshold, I have to begin to use quantum computation. But even then, going for a month or a year, and then how many qubits do I need? Physical qubits, we have QPUs with 10, 100, maybe bordering on 1,000. I need 10 million. I need 100 million. That's where we were. We knocked it back down. We knocked off a 0 or 2, but we're still here at between 1 million and 10 million qubits in order to solve a problem that we care about. That molecule up there is FOMOCO. It is a key catalysis. How do we do great chemistry to give us that next fantastic fertilizer technology so that we can wean ourselves off of petroleum-based fertilizers and understand how we feed 8 billion people and still sustain the environment in which they want to live. So knocking off some zeros, we're doing some great work, but still, we're still at some pretty challenging levels of integration. So this is where we think about, again, when we want to talk about when, we want to show the progress we've made. Now, we started here back in the 2014, those very early systems. We come up here, and what we wanted to get to, again, tens of millions of qubits, and so we hoped we would be on this curve. We were on this curve, but even then, it's still been flattening out. So there's something that has to happen. Right now, we really need to figure out how do we get to this new trajectory? How do we establish an exponential growth in capability? And that is going to be a really challenging problem. So that's the next question. Who and how? We know where to look for the applications. We are beginning to understand how to predict at least the date for a date, but who do we have to get together? Who needs to be on our team? Who do we have to draft in order for us to crack that nut and change the trajectory of that curve? So first we'll talk a little bit about those challenges. 3 big challenges we have with quantum computation. The first is noise. It is that the universe is against us. What we wanted to do, what Professor Feynman told us we should be doing, is taking a quantum mechanical system, one that we can control, one that we can manipulate, separate away from the rest of the universe, but the rest of the universe doesn't like that. It wants to get in there. It wants to jiggle the results. It wants to shift the odds. So whether it is vibration, radiation, heat, light, all of these things come in and they confound the quantum system. They swamp out the quantum behavior of those qubits. So how do we reduce the noise? How do we get a better qubit? The second piece is error correction. Now, I know a lot of us are familiar with error correction. We think about error correction in memory. We think about error correction on our networks. And we think about, well, if I add an extra bit or 2 every 8, I'll get to a robust error correction system. When we're talking about qubits, and this is where those millions come in, how about 10,000 qubits, 10,000 noisy qubits, I pull them together, I get 1. I get 1 qubit, and that's where those numbers get really big. So understanding how we correct these systems. Finally, scaling. If we really want to solve a problem that we care about, that's where you saw those numbers. Those numbers are measured in millions. The run times are measured in weeks, if not years, and we know from experience what it is to create an exascale system that can run for weeks or years, all of that error checking, all of that correction. So how do we pull together, first to talk about every be brutally honest, talk about every engineering challenge that we have as we go from 1,000 to 10,000 to 100,000, and that's probably about as big as we anticipate one quantum processor to be in, and then how do we scale up 1, 10, 100 of those quantum processors and stitch them together into a distributed quantum system. That is the quantum supercomputer. So if we double click into those challenges, the quantum processing units, they won't likely be anytime soon something where we have 100, 10 or 1 or 10 million qubits in a single device. We need to be able to distribute the computation just like we do with the GPUs, just like we do with the CPUs. We need to stitch them together. Now the challenge again, classical information. That's what we have to connect up these devices right now. So how do we intelligently partition a problem down so that we minimize the amount of classical information, minimize that transmission from the quantum domain to the classical domain and back again. The second challenge is that error correction. How do we have this really tight control loop? You know, when we manipulate a qubit, it might be something zapping it with a precisely shaped pulse of microwave energy. That's how we manipulate, that's how we program, that's how we measure, that's how we get data into and out of these quantum systems. And understanding that is a massive, real-time, floating point intensive classical computation. And the last piece is, how do we make today's application teams productive over these systems? They know how to create great applications, get great engineering science outcomes out of today's supercomputing. How do we build a bridge? Because the quantum natives, the ones who cut their teeth on probabilistic computing, they're probably, maybe they're in grade school, they might be in preschool right now. We might need to wait 2 generations, 20 years perhaps, until that group comes into their own, and they'll be programming these systems natively. They'll think in probabilistic computing because that's how they grew up. Until then, how do we make today's systems more productive? How do we make today's individuals productive over those systems? And that's really formed the research agenda that we've had here over these last 5 years at Hewlett-Packard Labs. We started, back 15 years ago, put the work on the shelf. Now we're re-entering the conversation, and we know that this has to be a group activity. We know we need to find, so first partner for us at HPE Labs was our own HPC AI and business unit, the teams that make literally the world's fastest, the world's most performant, the world's most efficient and sustainable supercomputing, because we'll need all of those technologies. Then we need to find those innovation partners. The low-level quantum hardware teams, absolutely, because we're not going to restart our low-level nitrogen vacancy on Diamond Lattice work. We will partner across all of the quantum computing modalities. There's about a half a dozen different ways to make a qubit. All have pluses, all have minuses, and for different parts of different problems, we'll need to incorporate each one of those kinds of technology to really get the most efficient and most complete story that we need to have to tackle a problem on quantum. Now, we're still doing the quantum inspired. We talked about that one. There is a way, as a parallel solve, to attach enterprise outcomes to quantum and quantum inspired classical supercomputing hybrids. Last piece, physics-based generative AI. Just a little teaser for some of the most advanced research that we have going on. Our emergent machine intelligence team at HPE Labs is exploring if I can solve a traveling salesman problem, and that's one of the ones that quantum is aspiring to, and if maybe we solve it faster by repurposing our photonic elements for quantum-inspired classical computing, I can solve a traveling salesman problem. I can also do deep reasoning. I can do deductive logic. I can do first-order logic because I can do a satisfiability problem. Now that can complement the large language model. So inductive reasoning from large language models, deductive reasoning from quantum-inspired classical computing and the physics-based generative AI. So really interesting research. They all come together, but we know that this has to be a team sport, and this is our team. Here we have 11 partners across industry, academia, national labs, really a broad swath, all the way down to semiconductor processing, all the way up through applications, and you can see a large group of us came together and we wrote this intensely provocative position statement, how to build a quantum supercomputer scaling from hundreds to millions of qubits. And again, this is where the title came from. We wanted to be brutally honest what engineering challenges, what do we need to do at each time we add a zero, what are we going to face, and how do we solve it as a community? And this is, all of those things that we need to do. Multi-physics design and simulation. Imagine having 100,000 of these quantum devices immersed in liquid helium at millikelvins, all being irradiated by microwave radiation pulses, because that's how you interact with a qubit. That's going to be a tremendous simulation, an EDA problem, an integration problem, a physics problem in the data center, and solving it there is even more challenging. Semiconductor process fabrication and tools. We want to use every tool that we have in scalable semiconductor processing, but a lot of them are going to need a little bit of tweak, so we need to have that team on board as well. All those quantum modalities, each wanting to have that precise real-time control, linking up to all of that GPU, CPU, and AI accelerator, but then down to application-specific pulse control. We got a partner there. All those compilers, all that quantum software work, and then above that, the exascale infrastructure, the CPU, the GPU, the slingshot fabric. That's how we're going to stitch all these things together. Above that, how do I take a problem I care about and break it down into the necessarily quantum pieces and into those classical pieces? And then inside of the quantum pieces, which one should go to a superconducting qubit? Which one should go to a trapped ion qubit? Taking each of these quantum modalities, capitalizing on its best contributions to a specific problem, and finally, again, applications. Back to the where, back to the question of solid-state material science, back to the questions of chemistry, back to pharmacology, drug discovery, all of those elements where today we are forced to use experimental science, physical experimentation, and we want to get to what we have in so many of the other engineering and scientific disciplines. I want to have it happen in the computer. I want it to have it happen marshaled together and interdisciplinary solutions driven by AI agents, and that's where we hope to get to. So that is the when, that is the where, that is the who, and that is the how. But in the last couple minutes, I want to circle back to our one known example of an algorithm that takes a little bit of classical data, has an exponentially improved quantum algorithm, and produces a little bit of classical data out, and that is Shor's algorithm, and that is the question of am I safe? Am I safe here, knowing that we've got these quantum systems on the horizon? What should I be doing? Now, this is where we look to Professor Shor and his integer factoring algorithm, and that means that quantum algorithms exist. They have been proven to be able to break cryptographic algorithms on which we depend, not only for protection. It's not just about encryption, it's also identity. When I take out my mobile phone and I turn it on, I authenticate to an access point, authenticate to a 5G, 6G. All of those actions depend upon public key cryptography, and that is what this breaks. So the Global Risk Institute, every year they do a survey, and this is their most recent survey. 50%, this is Vegas, so we got to talk about the odds. 50-50, even money, 2039, someone, somewhere in the world will have what we call a cryptographically relevant quantum computer. And by that we mean something that can take an RSA 2048, a 2048-bit cipher, and crack that cipher in one day. 50-50 even odds. And as a result, we've been working hard. And NIST, National Institute of Science and Technology, produced the FIPS, Federal Information Processing Standards. So we knew how. Now we have standards. We have post-quantum cryptographic standards. And if you got a chance to visit the Sphere today, you heard Antonio talk about ILO 7 ProLiant Gen 12. We started the conversation with that team about 4 years ago to prepare for this day, because right now, governments are beginning to publish timelines, and whether it is here in the United States, in Australia, the timelines are, here we go, January 2027. All new acquisitions are going to be compliant against the demands to incorporate post-quantum cryptography. 2030, all equipment and services cannot support it, phased out. So when we think about ProLiant, you heard Antonio tell the stories about how many people are still running Gen 8 ProLiant. Well, I have to imagine that a Gen 12 ProLiant is going to be healthy and active in 2029 and 2030. That's why we had to take the steps, and we were speculatively executing. The standards just came out this year, but we've been working for 4 years in order to prepare ourselves for this date so that we could then offer you the protection, post-quantum cryptography protected firmware upgrades, because the keys are in the silicon. And when you're talking about keys that are baked into silicon, you need to be able to think this far ahead. So right now, we expect, and this is not just here in the US, at this point, we expect 2026, that's when you'll see EU regulations also come out, but 18 member states in the EU have also said 2029, 2030, those are the dates in which you need to have incorporated post-quantum cryptography or have adopted a provably safe alternative method. So tick-tock, it's time for you and the enterprise to have this conversation right now. So that's where we have some resources for you. We have worked, as I said earlier, we've been working at the World Economic Forum. That combination of the cybersecurity practice and the quantum development teams have been working for now several years and producing toolkits for you to begin to have that conversation. Now, our overall recommendation is for all of you, this should be a CISO-led experience because this is a cybersecurity, fundamentally a cybersecurity challenge. And in many ways, this is almost the best thing that could happen. Because, and so for many of us, we've been thinking about the potential of, what does it take? I might have my keys compromised. I might have my signature authority compromised by bad actors, by coercion, by a variety of mechanisms. And now this is that opportunity for us to have this be a catalyst to adopt a crypto agile development methodology. We grow here at Hewlett-Packard Enterprise both organically and by inorganic acquisition as we're bringing in more teams. More teams each has their own cryptographic history. And this is a chance for us to rationalize all that, to understand, okay, where do we have to adopt post-quantum cryptography? Where do we want to move, even if traditional cryptographic methods are still provably safe? How can we use this as an opportunity to have an opportunity to change to really cryptographically safe and agile methods? How do we bring everyone back into the fold? So in many ways, this is a great opportunity for you to start a conversation. Maybe it's overdue. Maybe you should have been having this conversation before, but here's a great reason to start. To engage with your CISO, engage with your line of business. We're having the same engagement with our vendors, as well as our partners, as well as our customers, as well as our team members. So one of my fellow HPE fellows, Nigel Edwards, who is here this week at the HPE Labs Pavilion talking about confidential computing, he's the head of our internal post-quantum cryptography center of excellence. So he's having conversations across the entire breadth of the company, both internal, external operations, product development. We're starting all this conversation right now. So I think there's a fantastic opportunity for you as well. Take a page out of these books. If you have any other questions, we're happy to start that conversation. But it's just really a great opportunity for you. So, net of it, if you have a fume hood, if you have an IWA station, if you wear a lab coat to do your work, then you might be a candidate for the very first quantum utility applications. If you're dealing in a lot of classical data, if you want to do machine learning on a lot of classical data, conventional classical computing is probably going to be your best solution for quite some time. But again, this is not a competition between quantum computing and classical computing. It is understanding how we have the same facility and engineering skill and scientific discovery, regardless of whether it's classical physics or quantum physics. They need to be melded together, and really that is what we're leading across our research community to try and provide that hybrid solution, that bespoke quantum classical meld that will really solve important problems. Thank you.